If I were to ask you to render a realistic video using only a setPixel function, how would you begin? Let me clarify. You will need to create a 3D world and a camera capable of capturing your scene. There are two main approaches to achieve this. One by projecting 3D objects directly on your viewport, and the other by tracing the path of many rays. In this video we'll focus on the second approach. The first baby step involves creating a camera to cast those rays. What's the main idea behind this concept? You have a rectangle which represents your viewport and a point camera origin. The viewport is just like the window through which you're peering into a 3D world. Of course, now this window needs to have some kind of dimensions, so for its size I will choose some arbitrary numbers like 16 for the width and 9 for the height. The ratio between 16 and 9 is called aspect ratio. It basically defines the shape of the camera. In ray tracing, you want all your rays to start from the camera origin and pass through your viewport. That point camera origin is vital since it defines the position in 3D world of the camera, and that's why it is called the camera origin. Again, all the rays will start from this point. The viewport center should be 1 unit in front of the camera origin. Now get those two concepts and finish up the camera. It has a vector 3 origin and a rectangle viewport. Of course, now in the future the camera will get very sophisticated, but we have enough for now. Let's get to shooting rays. Each ray must return some kind of heat info, which represents the ray trajectory output. We can turn the heat info into colors, and shooting a ray for every pixel of course colors every pixel, slowly forming an image. The issue is that this process repeats for every frame, which is pretty expensive to compute, but we'll have to deal with it. Now when it comes to defining rays, they have a ray origin and a vector 3 ray direction. We want to cast those rays starting from the camera origin, so the ray origin is obvious, but calculating their direction is slightly more complicated. It involves matching every pixel on the screen to a point on the viewport rectangle. To do this, we normalize the screen pixels, turning the coordinates into percentages. Subtract 0.5 to center the origin and multiply by the viewport dimensions. In a nutshell, we've changed from screen space to viewport space. Don't forget about the z component, which in this case should be -1 since the viewport is 1 unit in front of the camera. Now, since the entire idea of ray tracing involves calculating ray intersections, we need a way to define a point on a ray as efficient as possible. If you think about it, we can move t units in the ray direction to describe any point on the ray. Again, this means that starting from the ray origin and going a t amount of units in the ray direction results into a point. So any point P on the ray is defined as ray origin plus ray direction times t, a very useful formula. It's important to know that if t is negative, then the point is going in the opposite direction. Now finally, we've casted the rays, it's time to draw something. At its core, a sphere is a center and a radius. It is defined by any point r distance away from the center. We can safely see that the distance from P to C is equal to r, where P and C are the vectors of any point on the sphere and the sphere center. And by the way, we're going to switch between points and vectors quite often, so get used to that. This results into the following equation. The point of incorporating spheres into our scene is to provide a basic object that can be detected by rays. If a ray touches a sphere, we color the ray's pixel as gray. Doing this for every pixel should result into a representation of the sphere. To know if a ray hits the sphere, we can verify if a point on the ray can be r distance away from the sphere center. So P is the intersection of the sphere and ray. This point belongs to both of them. P can be described as ray origin plus ray direction times t because of that ray formula, which I will refer to them as A and B for simplicity, so P is equal to A plus B times T. Substitute in for P and you get A plus B times T minus C times A plus B times T minus C is equal to R squared. Now using some vector algebra you get this sinister thing. Lucky for us, this is just a quadratic equation, so we can solve for it using that 8th grade formula. But we just want to know if the ray hits the sphere, nothing more, nothing less. Let me tell you that the number of real solutions of that equation happens to be the number of ray intersections with that sphere. That's actually pretty exciting because it means that if the discriminant is positive, then we have touched the sphere, so we can return gray, for example. Earlier we've detected if a ray hits the sphere, now it's time to detect where. The quadratic from earlier should have two solutions if we hit the sphere, not necessarily distinct. As you might know, we can calculate them using negative b plus minus discriminant divided by 2a. And this happens to return t. And what do we know about t? It describes the point on the ray. So the solutions tell us the values of t where the ray hits the sphere. That's really useful, because we can use that description we've made earlier and plug in those two solutions, right? That will work, I guess, but we only care about the first intersection. So we'll use only the lowest t, which is negative b minus discriminant divided by 2a. This point we've calculated represents the pixel's point on the sphere, or the intersection with the sphere. That's a very useful coordinate, and we'll make use of it in the future. A surface normal is a vector perpendicular to a given object. Consider a plane for a second. A normal will be a vector that points either up, either down. Normals are fundamentally raytracing. They tell us information about the surface the ray just hit. That's huge. Those normals help us reflect light, shade objects, they describe the interior and exterior of something, and much more. And if there is one thing you should keep in mind, is that the normal represents the concept of up or down. In this series we'll focus on the normals that point up. I haven't addressed the normal's magnitude, and that's because it might represent the curvature of an object or simply their unit vectors. To keep things simple, we're going to pretend they're unit vectors all the time. So again, in this series normals are vectors that point in the exterior of a given object, and they have a length of 1. Asking what's the normal of a given point P on a sphere is like asking which way is up. We can visually see that the vector that starts from the sphere center and lands on P points in the exact same direction as the unit vector we're trying to find. So we can say that the normal is P minus sphere center? Not quite. As I said earlier, a normal vector has a magnitude of 1. This one has the same length as the sphere radius. So dividing this vector by radius will scale it until it has a length of 1. This is the last concept of this video and probably the fanciest so far, which is shading a sphere. What we want to achieve is pretty simple to describe: a sphere that has one side illuminated by some light source and the other side dark. If you think about it, describing a light source isn't the scariest task. We can just refer to it as a direction and an intensity. The direction is, of course, the orientation the light is emitted, and the intensity is even more obvious. The higher the intensity, the more illuminated the sphere will be. We need a way to influence a pixel's color depending on this light source we've described. We know that each pixel determines a point on the viewport, and we know that a pixel that represents the sphere determines a point on the sphere, right? After that's how we found the pixel's color. So the question is, how the light source interacts with the points on the sphere. We can get even fancier since every point has a normal. So how the light source interacts with the sphere's normals. Damn, that really sounds way complicated, but don't you see something weird here? We wanted to shade the sphere in a way that one side is illuminated and the other side is dark. Take a closer look at the normals. They actually describe a pattern. The normals that point in a direction similar to the light source tend to represent darker pixels, and the normals that are going the opposite direction represent lighter. Similarity of directions? I don't know about you, but this definitely reminds me of something. The dot product, the function that describes how similar two vectors are. And what's more exciting is that the dot product's output is a number, and judging by the logic from earlier, the lower the number is, the more different the vectors are and the more illuminated the point is. This function literally returns a number that tells us how dark or light that point is. And as you might know, the dot product's value might vary. That's a big problem, since we need some kind of preferred range to work within. The good thing is that using the dot product on two unit vectors returns a number between -1 and 1, perfect for what we need. The next steps are pretty obvious and simple. First, invert the value, since the normals that point in the opposite direction should be lighter. Take that value and scale it by the light's intensity. This gives some control on the amount of light we are emitting, and to prevent negative number issues, you can just clamp this number. This makes it by force positive, and we can safely use it to influence the pixel's color. To finish things off, multiply it by the color. And finally the math is brought to life, and we can actually see how the normals interact with the light shading our sphere. If you want to have even more fun, you can set the light's direction to something like sine of time 0 cos of time. If you made this in real time, then using the time variables will make your scene more entertaining. Well, that's it for now. If I continue animating this video, my brain will explode, and I don't know about you, but I would like to keep my cognitive function working. Now, please remain for a couple of seconds, because I want to mention that you can help me make better videos by giving me constructive feedback. For example, you can comment, your animations are too fast, or you sound like shit. That would help me a lot, and I would really appreciate it. The music in this video is made by Very Bad Audio. I hope I said that right. And it is copyright free, and it's really amazing. I've been using his or her songs in my videos for quite a while, and to be honest, they are my favorite no copyright tracks from YouTube. I hope you learned something today, and see you next time.